Good afternoon, everyone. I am Shreya, one of the TAs for this course on Essentials of Data Science with R software. And today we'll be discussing some concepts which were discussed during week 12 lectures and some problems related to those concepts. So, without any further ado, let's get started. So, week 12 was all about testing of hypothesis. Now, what do we exactly mean by testing a hypothesis? A hypothesis is like a claim, alright? So, we have some claim and then we are going to test whether our claim is true or whether that is false. Now, whenever we make some claim, that has to be backed up by data, alright? So, anything that we would like to see or we would like to assume, we would want that to have sufficient evidence from the data that we have at hand so that we can make a clear-cut decision. So, as I was saying, let us assume that we have introduced a new medicine, okay, that is going to reduce frequency of, let's say, indigestion events. Alright, so then if I have to test the efficacy of that medicine, the frequency or number of times I am getting digestion problems after ingesting that medicine or after taking that medicine, that should decrease. Alright, so we would want to test that. Okay, first thing is there is no effect, it's not acting properly, it's not effective for me, it is not reducing. So frequency of, let's say, occurrences of indigestion, that remains the same before and after. Okay, and our alternate is something that we would like to believe. We would like to reject our null hypothesis in favor of the alternate hypothesis. So what is our natural intuition? If we want a medicine to be effective, we would want that medicine to lower the frequency of indigestion events. Okay, so that will be my alternative hypothesis. So here we have introduced two concepts, which is H naught, which would be the null hypothesis, or in effect it would be indicative of a no effect situation, and this would be the alternate hypothesis, that we would something that we would like to believe in, and we would reject null in favor of this one. Okay, so there are always two hypotheses that we are considering, and this rejection or acceptance of null hypothesis has to come with a certain certainty level. Okay, so only when we can say that we are, let's say, 95% confident that this null hypothesis can be rejected in favor of this alternate hypothesis. So we want that quantification. Alright, so we have learned the definition of hypothesis, and what we are doing statistically. Hypothesis will make a claim about a population parameter theta. Okay, population parameter theta, which is actually unknown. Alright, it's a claim or an assumption about a population parameter. So let's say if I want to judge or assess that the average rainfall in the months of July is something. So we don't know what will happen in the future, but we want to make an assumption about the average rainfall based on the past data that we have had. Okay, so that is sort of an example. Alright, Next, what we have learned is that what do we mean by a simple and a composite hypothesis. Alright, so if the distribution, simple means that the distribution is completely specified given given h naught. So what do I mean by this is, let's say I have an x variable which follows some normal mu and sigma square equal to 1. Okay, so if my null hypothesis, this is always with respect to the null hypothesis, okay, that is h naught. Alright, so if we say that h naught mu equal to 7, then under h naught this distribution is completely specified. It is from normal mu 7 sigma square equal to 1. This is completely specified with no I would say that no unknown as such under h naught, given that we are assuming h naught is true. So under h naught or given h naught is true, if the distribution is completely specified, then we say this to be a simple hypothesis. And when we say this to be a composite hypothesis, if the distribution is not fully specified. Okay, so here it should be distribution fully specified, and here not fully specified. As an example, let's say if we say h naught mu should be greater than equal to 7. So it could be anything. It could be 7, 7.2, 7.5, 7.9999, 7.00001, could be anything. Okay, so this distribution is not fully specified when we have a hypothesis like this. So this is the case when this hypothesis, we'll call it as a composite hypothesis, okay, because it does not completely specify the distribution. Okay, now when we are doing or testing any hypothesis for that matter, we would want to define certain decision rules, okay, that would specify whether we should reject or accept the null hypothesis. One more thing I should mention over here. Here accept doesn't mean that I am fully agreeing with h naught. Here accept means that I do not have sufficient evidence to reject h naught in favor of ha. Okay, so there is a subtle difference. It doesn't mean that h naught is true. From the data, what it means is that from the data we don't have enough evidence to prove that okay, h naught can be rejected. We are lacking there. We are lacking in terms of evidence. It doesn't mean that h naught is the ground truth. Alright, okay. So as I was saying, what should we do? Should we reject or should we accept? This is one question. Should we reject or should we accept h naught? Now this can't be random. Okay, so we have to make certain rules, okay, for our decision. So let's say if we have this region, let's say this is my decision space, okay, this one let's say is my w and this is w complement. Alright, now if we have x1, x2, xn, alright, then certain function, because our decision would be guided based on the sample at hand, whatever evidence we have. So this sample, whatever we have, is sort of the evidence at hand. Okay, so if some function of these samples, let's say it belongs to w, I am going to reject h naught, and if it doesn't belong to w, then I am going to accept h naught. Okay, Now note this W and W complement are mutually exclusive. Okay, there shouldn't be any gray area. It should be clearly defined. Okay, if it falls within W, I am going to reject. If it falls, if it doesn't fall in W, I am going to accept. Okay, now how do we do this? This construction of, let's say, W or W complement, that defines what my decision would be. So W is actually my critical region. Okay, and W complement is the region of acceptance. Okay, now how should we frame this decision rule? We could end up in sort of making the wrong decision as well, but the goal is not to make wrong decisions. So let's say if this is the, so if we consider the confusion matrix over here, or this 2 cross 2 contingency table, this is accept H naught, this is reject H naught, and here it's the ground truth. Okay, and this is our decision, let's say. Okay, ground truth is H naught is true versus H naught is false. Okay, so if H naught is true and we accept, then we are landing up at a correct decision. Okay, I hope I'm audible and the screen is visible. Alright, so before I move further, I was just giving some introduction about the week 12 concepts before moving on to the actual problem solving. So if you have any questions from the previous lectures or previous assignments, you can ask me now if there's any doubt.
Hello.
Hello? Yes, ma'am.
First question from the previous assignment.
Which one?
First question from the previous assignment.
First question. All right.
Ma'am, I solved that question and all the estimators are consistent in this question, but as per the solution given us, uh, first I think option A only estimator mu1 is consistent estimator.
Yes, that's
Others
because,
are.
yes.
Is this solution is correct?
Yeah, the solution is correct.
But as per the other TS lecture, all the three estimators are consistent. That this was taught earlier. I have taken other TS lecture also. Both the other TS taught us that all the three estimators are consistent.
I understand, but then this, it doesn't go in probability to 0. So this confusion was cleared in the discussion forum. I don't know if you have tracked it or not.
Yes, ma'am. The other also put this question in the discussion forum that But I did not go to the solution of that. So please,
So the thing is, you have to prove. Okay.
so how
So
we should go in this question like this?
yes, so if an estimator is going in probability to theta, only then we say that this is a consistent estimator. Alright, so let's say here you have probability. So this should be it. Tn minus theta given should be greater than, for all epsilon greater than 0. Tn minus theta greater than epsilon, this probability should go to 0 as n tends to infinity. Alright. Now, this one you can write it that probability Tn minus theta greater than epsilon, this is actually equal to probability Tn minus, so this is a positive quantity, alright. So this we can write, or rather, let's say one second. This one we can write as probability Tn minus theta whole square greater than epsilon square. And by Chebyshev's, this is less than equal to expectation of Tn minus theta square by epsilon square, which is nothing but the MSE of Tn by epsilon square. Now if the MSE is going to 0, then only we can say that this is consistent. Alright, and MSE is variance plus bias square. So for all the
both the conditions should be followed in
yes,
this.
both the conditions should be followed.
Okay.
So if variance
We
is,
have also asked for the same, that both the conditions should follow, but they have told that either of the conditions should be followed. If
no,
either of the
actually this
conditions should
entire
be followed.
quantity should go to 0. This is the
Okay.
definition, okay.
Mm-hmm.
So if you don't have any bias, so for x bar what happens, expectation of x bar is mu, so this bias term is already 0. So if variance is going to 0, it's 0, it is established.
Okay.
Okay. Anyway, if you even if you just look at this
Ma'am,
thing,
please solve it so that I have a better clarification on this question.
so variance of b mu to you understood what is there. Okay, so okay, fine, this is x bar by, can you tell me what was the, okay, I'll just do n to the power 3 by 2, n to the power 3 by 2. Alright, so MSE of x bar by n to the power 3 by 2 is actually variance of x bar by n to the power 3 by 2 plus bias of x bar n to the power 3 by 2. Okay, so bias is what? Bias is expectation of x bar by n to the power 3 by 2 minus mu. So this is mu by n to the power 3 by 2 minus mu. So this is mu 1 by n to the power 3 by 2 minus 1. Alright, and variance is how much? Variance is 1 by n cube. This one is 1 by n cube. Variance of x bar is sigma square by n. Alright, so as n tends to 0, MSE of this Tn is actually sigma square by n to the power 4 plus bias square. So this would be mu square 1 by n to the power 3 by 2 minus 1 whole square. So as n goes to 0, this goes to 0, this term goes to 0, and MSE goes to mu square. So if mu is 0, then it is consistent. If it is saying that it is going to, let's say if mu is exactly 0, then it is consistent, but we don't have a clue on what mu is. It is going to mu square, and thus it is not consistent. Similarly for the next one. Is it okay?
Yes, ma'am.
Alright. Anything else?
No, ma'am.
All right. So let us just quickly brush up week 12 concepts and then we'll jump on to the question answers. Alright, so I was just explaining what we mean by a hypothesis. It is actually nothing but a claim that we make, and we have to just prove whether our claim is true or false. Alright, and we cannot take this judgment randomly. Our decision has to be backed up by data. So usually what happens, H naught is denotes the null hypothesis, which gives an sort of what do I say, which claims that there is a null effect or no difference in previous and current states. For example, if we are, let's say, introducing a medicine, okay, that treats you for indigestion. Now what do you expect? If the medicine has to work, then we would expect that the number of times you are getting that indigestion will reduce after you take the medicine, right? So null hypothesis in that situation would be a no effect thing. So frequency of indigestion doesn't decrease, it remains the same before and after. That would be a no effect or null hypothesis. An alternate hypothesis is usually the one which we would like to believe in, because when we test for hypothesis, we actually reject null in favor of alternate. It doesn't mean that null is the ground truth, okay? It doesn't mean that there is no effect. If we are rejecting H naught, it doesn't mean that that the alternate hypothesis is the ground truth or something like that, okay? What it essentially means is that we have enough evidence to reject H naught in favor of H1 or the alternate hypothesis. Okay, so there's a subtle difference that please keep it in mind. And what the hypothesis is actually doing is, it is claiming about a population parameter which is unknown. Okay, and if under the null hypothesis the population parameter it is making a claim about is that parameter completely specifies the underlying distribution, then we call it as a simple hypothesis. And if it doesn't completely specify the distribution, then we say that it is a composite hypothesis. For example, if x follows normal mu sigma square equal to 1, if H naught is mu equal to 7, then under H naught, that which means that if we assume that H naught is true, the distribution of x is completely specified. But that is not true when mu is greater than or equal to 7. It could be 7, 7.1, 7.2, 8, 9, 10, anything under the sun, but greater than equal to 7. So this distribution is not completely specified under this H naught. Alright, so such hypotheses are called as composite hypothesis. Now the next thing that I was talking about is formulation of decision rules. So if we should accept or we should reject, this decision can't be random. It has to be based on the data. Okay, so this data is actually the evidence. Alright, so usually what we do is we define a decision space such that this point x1, x2, xn, if that belongs to this W, then we call it, we will take the decision that we are going to reject the null hypothesis. And if it falls in the complementary mutually exclusive region, then we say okay, we are going to accept. So this region where either the point falls in this n-dimensional region or some function of it, it could be a one-dimensional function, if that falls in this region, then we say that we are going to reject the null hypothesis. So this is the critical region that we are talking about. It's critical because it is critical for rejecting the null hypothesis. So if it falls here, this point, the x1, x2, xn, if it falls here, then we are going to reject or we are going to accept. Now, how should we reject or accept? So there could be 4 scenarios. let's say on this axis we have the ground truth that H naught is true and H naught is false, and this is our decision: accept H naught or reject H naught. So if H naught is true and we are accepting H naught, then we are taking a correct decision. If H naught is false and we are rejecting H naught, then also we are taking a correct decision. Okay, but rejecting H naught given H naught is true, this is absolutely a wrong decision, and this is also a wrong decision. When we know H naught is false, but then we are falsely accepting. Okay, so both of these are wrong decisions. But rejecting H naught given H naught is true is actually what we call type 1 error, and accepting H naught when H naught is false is the type 2 error. Alright, this is specified by alpha, this is specified by alpha, this is specified by beta. Alright, now which one should be, so out of these two, the type 1 error is, the problem should be formulated in such a way that type 1 error is more dangerous. Okay, so just imagine a situation where where the example is of a convict. Okay, a convict who is getting judgment. So if he has not done any crime, okay, so H naught is, let's say, no crime. Alright, H naught is that the convict hasn't performed any crime, and this is that person must have must have done some crime. Okay, so out of these two errors, this is like the decision is to execute, let's say. So this decision would imply that we are executing on an innocent person. Okay, and this would imply that we are letting go of someone who has done the crime. Okay, now even though both the decisions are wrong, but this is a more severe one because we are punishing someone for something. Punishing an innocent is a is more looked down upon, right? So because of this region, type 1 error and type 2 error, we should formulate our null hypothesis in such a way such that the type 1 error is more dangerous. Like rejecting H naught when it is true, this has far severe, this should ideally have far severe consequences than accepting H naught given H naught is false. Alright, this is how we should frame the hypothesis. Now, another, if what happens if we want to, so the goal should be to keep everything less. Alpha, type 1 error should also be less, type 2 error should also be less. So if in an ideal world, if we could control both of these, then it would have been good. But it has been shown that it is not possible to control for type 1 and type 2 error simultaneously. Okay, so if we try to decrease one, the other one inevitably increases after certain point. Okay, so if we believe that we are going to control both of them simultaneously, that is not possible. So what is usually done is that we set type 1 error less than equal to some cutoff. Okay, so we fix it that okay, we are not going to allow more than this percentage margin of type 1 error. And once we have fixed that, next goal is that we reduce the type 2 error. Okay, and reducing type 2 error is actually increasing power of a decision. So what do I mean by power? Power is the what do I say? Power means that I am taking a correct decision. I am rejecting H naught when H naught is actually false. Okay, so that is what I mean by power. It is 1 minus beta. So what do? We fix alpha type 1 error at some point, and then we try to maximize the power, and that is how we land up at the test rules or test decisions that we actually have. Alright, so as I was saying, this is the definition. Type 1 error is probability of rejecting H naught given H naught is true. Okay, type 2 error is probability of accepting H naught given H naught is false. Okay, sorry, not probability, this is the error. Now what do we, the size is the probability of type 1 error. Okay, so this is actually probability reject H naught given H naught is true. Alright, and this is actually what we call as alpha, or our level of significance. Okay, to be very specific, size is always the probability of type 1 error, and size is less than or equal to alpha, but some books will specify that size is actually alpha, what we set our level of significance as. Alright, okay, and if somebody asks for size of type 2 error, this usually denoted by beta, this is probability accept H naught given H naught is false. Alright, and power is actually 1 minus beta. This is a good criterion because we are rejecting H naught when we know it is not true. Alright, okay. So next we learned about the Neyman-Pearson lemma, which says that, which specifies the rule for rejecting H naught. Okay, so what it says is that if this is the likelihood of theta naught given x1 to xn, then the ratio of the likelihoods under theta, so let's say H naught is theta equal to theta naught and H1 is theta equal to theta 1. Alright, so likelihood of theta naught given the data by likelihood of theta 1 given the data, it should be less than equal to k. Okay, and such that wherever this holds, so let us assume that the space where this holds true, where this L0 by L1 less than equal to k, this set we can say that this probability that x belongs to this C is equal to alpha. Okay, so this is what we call as Neyman-Pearson lemma. Okay, so we have to determine that the area where this likelihood is less than equal to some function k, and that k is defined in such a way that probability that this sample belongs to C is actually alpha. Okay, so this is what we learnt with respect to Neyman-Pearson lemma. And then the proofs were not actually given, but using this lemma we could formulate certain tests. Okay, so we learnt about two sorts of tests: tests for mean and tests for variance. Okay, so these were primarily two type of tests that we learnt about. Okay, and for each of these tests we learnt about some one-sided or two-sided tests. Okay, so let's say if we have our null hypothesis H naught as theta equal to theta naught. Okay, and versus H1 is theta greater than theta naught. So this is actually a one-sided test. Okay, or let's say theta less than theta naught. This is also a one-sided test. But if we have theta not equal to theta naught, then we have actually two-sided tests. This theta could be variance, the theta could be mean, could be anything. Alright, some population parameter. Okay, so when we have one-sided test or two-sided test, what actually happens? So let's say if we have a two-sided test. Okay, so if the distribution of test statistic is this, okay, if we have a two-sided test, we would have this point and this point, the area above which this and this area, let's say alpha 1 and this, let's say this is alpha 2, these two areas should add up to alpha, which is the level of significance. Okay, and these cutoff points are actually my critical values, and this region should be my acceptance region. Okay, so let's say this is the distribution of t statistic. Alright, so if it falls, the value of the statistic that is observed given the data, if it falls within this range, then we are going to accept, but if it falls here or here, then we are going to reject. Okay, but what happens in case of a one-sided test? In case of a one-sided test, let's say this is the distribution of the test statistic. Now under H1, if H1 is true, our test statistic should fall in this region, or it could also fall in this region. Okay, so under H, if it falls within the acceptance region, then we accept, and if it falls within the rejection region, which is usually one-sided, okay, either this side or that side, if it falls like that, then we can say that this is a one-sided test and take decisions accordingly. Now one more thing to note is that, let's say this this is not that common to get in questions, but let's say you have something like this, mu equal to 5 versus mu greater than 5. Okay, so the test statistic based on Neyman-Pearson theorem it is such that the test statistic will also, if it is greater than some t critical, it has to be H naught is rejected. But it does not mean that whenever I have some theta value which is greater than 5, then my test statistic should also bear the same greater than signature. That is not always true. Okay, so that will depend a lot on the distribution, like how we are constructing this likelihood function. What I mean to say is that if I have theta equal to some theta naught and theta greater than theta naught, then if here we have greater than theta naught, it doesn't necessarily, it doesn't imply always that the test statistic should also be greater than some critical value. This might be true, might be true, this might not be true. Okay, this will depend on the likelihood function that we are defining and less than equal to k, this ratio. How we are formulating this ratio, it will depend entirely on that. If we have greater than here as theta naught, it could very well happen that I have something t less than t critical as my decision rule. This is also very well possible. Okay, so just keep this in mind. Alright, so next what do we learn? We learnt about how to test for significance, and then we learnt about p-value. Okay, so p-value is nothing but, this is the estimated probability of rejecting the null hypothesis. Okay, so let's say if for a two-sided test, this probability t greater than t observed is actually my p-value, and if I have a single-sided test such that t greater than t observed is my rejection region, if my test is such, then probability t greater than, if t greater than some t critical is my rejection region, then t greater than t observed, this is my p-value, and if the rejection rule is t less than some t critical to reject, then p-value will be probability t less than t critical. The utility of using p-value is that it is very simple and straightforward in terms of decision. If p-value is less than alpha, then we reject. Okay, so if some program is giving you directly the p-value, then you did not worry, you can directly go ahead and reject the null hypothesis. Alright, okay. So now that we sort of understood, we learnt about certain tests. Okay, so the first one was tests for mean. Okay, now tests for mean can happen in two categories. Okay, when the variance is known and when variance is unknown. Alright, so when variance is known, we will go for a z-test, and when variance is unknown, we would go for a t-test. Alright, so I am talking about a one sample mean test. Okay, provided my sample size n is less than equal to 30. 30 is the usual rule of thumb number. Okay, but if n is greater than 30, we could approximate the t-test with a z-test also. Okay, so what I'm trying to say is that if we have large samples, then by the central limit theorem, every statistic can be approximated with a normal distribution. So in that case, we could perform a z-test. Alright, okay. So here is a summary of the types of tests and that should be performed. Okay, so z-test is to test that if the average of a single population is equal to a target value, and where we can do this when sigma is known to us. When sigma is not known, sigma is estimated by the sample variance. Sample variance, how do I get it? This is 1 by n minus 1 summation xi minus x bar square. Okay, so we get a s square, then we take s, and then it is important to remember we divide by root over n, not n minus 1. Okay, and then the t statistic has a df of n minus 1. Alright, same thing happens when we have a paired t-test, when the variance is not known. And we could also, when we have two samples, we could have a two sample test with pooled variance. The test statistic takes this form and it is a t distribution with this df. And if we do not pool the variance, then we use this statistic. Alright, so let us solve a few sums, then I think hopefully these ideas will be more clear to you. Alright, okay. So moving on to the first one. So here we are saying x1 to xn is a random sample from a population with normal distribution. This is the population mean. Which of the following is not a composite hypothesis? So this is following a normal distribution. Okay, and if nothing is mentioned, usually since here no question about sigma square is being raised, we would assume that sigma square is known. Alright, so given that sigma square is known, which of the following is not a composite hypothesis? So under which hypothesis is the distribution completely specified? This is this one, h naught mu equal to 5. Alright, so then this is the correct answer. This is not a composite hypothesis. This is a composite hypothesis because normal mu sigma square, even though we assume it to be known, this is not completely specified, not completely specifying the underlying distribution. Okay, so the answer is mu equal to 4 is the simple hypothesis. Alright, moving on. Let's say this one. Suppose an experimenter tests the hypothesis h naught equal to 0.8 versus h1 equal to 0.5 based on 15 Bernoulli trials. Decision rule is this: test statistic as the total number of observed successes and accept the null hypothesis if t is greater than 11. Okay, so then rule is what? Rejection rule is what? Rejection rule is t is less than equal to 11. Okay, now Bernoulli trials, total number of successes. So total number of successes in n Bernoulli trials, then t will follow a binomial distribution. How many trials? 15 trials, and the success probability is p. Okay, so this is p. Alright. Now what is the type 1 and type 2 error? So type 1 error is actually probability of rejecting the hypothesis given H naught is true. So probability t less than equal to 11 given H naught is true, that is p equal to 0.8. Okay, this is what? This is actually 1 minus probability t greater than 11 given p equal to 0.8. So we can just do it from our we can use our R to do this, or we can either calculate also. So this would mean 1 minus probability t equal to 12 given p equal to 0.8 plus probability t equal to 13 given p 0.8 2 plus probability t equal to 15 given p equal to 0.8. Or we could just directly do it here. It should be 1 minus p binom 11, n is this thing 15 and p equal to 0.8. So let us just find out. Can you see my screen, the R console? Yeah. So here 1 minus p binom 11, n equal to 15 or size equal to 15 and prob equal to 0.8. This is 0.648. That is the type 1 error. Okay, so this is 0.648. Alright. Now, same question, what will be the type 2 error? So here again, type 2 error is, error probability is probability accept H naught given H naught is false, or in other words, probability accept H naught given H1 is true. So this is what probability, what is the acceptance rule? T greater than 11 given p equal to 0.5. Okay, so this will be actually how much? This is also p binom. Oh sorry, this is greater than last one, it was greater than 11, p given 0.8, right? So this would be p1 minus p binom lower dot tail equal to false.
False.
Yes, so it will be 0.35. So yeah, this is 0.35. Okay, and this one is also the same thing. We'll do p binom, just this thing, 11, size is 15 but probability is 0.5, so it should be 0.017. This is 0.017. So this answer C is the correct one. Is it okay?
Yes.
Alright. Moving on. Here what is it? Suppose that 70 weighing machines made by a company can work on an average 1800 times with a standard deviation of 120 times. The decision for testing H naught mu equal to 1600 versus H1 mu less than 1600 at 5% level of significance is how much. Okay, so here we'll assume that xi is the weight of ith machine. Okay, so then we have n equal to 70 weighing machines. Okay, and sorry, we have 70 weighing machine that can work on an average 1800 times. So xi is the number of times ith machine can work. Alright, and we are, if mu is the average number of times the machine can work, this is our h naught, mu equal to 1600 and mu less than 1600. So first thing is, does it require is it a one sample test or a two sample test? This is a one sample test because we have one sample consisting of 70 units. Okay, so then here the test statistic is how much? This is x bar minus mu by sigma by root n. Okay, and sigma is how much? Standard deviation is given 120 because sigma is known. So the test statistic is a z statistic. Okay, minus mu naught, which under h naught follows a normal 0 1. Okay, so then this one, if x bar is way more than mu naught, then it would imply that, let's say this is a normal curve. Okay, if x bar is greater than mu naught, it means that it will fall on somewhere here in this extreme, and if it is very less than mu naught, okay, mu naught, let's say this is somewhere here. So if the difference between x bar and this is positive, then it will fall on this end, and if it is negative, then this would fall on this end. Now what is the decision? Mu is less than 1600. So therefore, since this is a one-sided test, our decision rule is so if mu is less than 1600, if x bar this is 1600, okay, so then if it is less than 1600, then this difference would be negative, so it would fall on, let's say, this extreme. Alright, so now we have to determine this critical point such that the area below this is alpha, that is 0.5, 0.05. That is our level of significance. We have given 5% level of significance. So now let us just find out this observed value, T critical, or sorry, not T critical, this should be Z critical. Okay, so what should this value of Z be such that the below area is 0.05? It is actually minus 1.64. Okay, and we can also find this out from here. So this would be Q norm, okay, that point such that area below it is 0.05. Okay, and since it is Z, mean of the normal distribution is 0 and ST equal to 1. Alright, so then this is how much? This would be minus 1.64. Alright, so this point is minus 1.64. So here our rule is, we'll reject H naught if and only if T observed is less than T critical, or rather than, let's say, Z critical, which is minus 1.64. Alright, Now let us calculate T observed. T observed is how much? X bar minus mu naught by sigma by root n. So how is this X bar? Okay, so this is 1800 times. Okay, X bar is given as 1800 and sigma is 120. So we can write this as 1800 minus 1600 by sigma is 120 by root 70. So this is 200 by 120 root 70. So this is obviously greater than 0. So it should be greater than minus 1.64. Therefore, what do? We fail to reject H naught and hence accept H naught. Is it okay? Any confusion, doubt? So then the answer is that H naught cannot be rejected. Alright. Shall I move on to the next one?
Yes.
Okay. Let's say this one. Suppose that an engine can pump on an average 185 liters of water per second. If 5 pumps are randomly selected and the water pumped by them is this, decision for testing mu versus H1 mu less than 185 at 5% level of significance is how much? So here also it's the same thing, we just have to calculate. So Xi is the water pumped by ith pump. X bar is the average mean water pumped. Alright. So the difference between previous one and this one is that the sigma square or SD is not known. So then the test statistic will be X bar minus mu naught by S by root n. Okay, and then the rejection rule will be reject H naught if and only if T is less than T critical. Okay, and what will be T critical? This should be that point in the T distribution such that area below is alpha, which is 5%. Okay, and T critical DF will be n minus 1. So let us just find out. Step 1 is rule, reject H naught if and only if T observed is less than T critical. Okay, step 2 is get T observed. T observed is X bar minus mu naught by S by root n. Okay, so this will be how much? Calculate the mean of these 5. 171.6. So if I just write mean, mean of 171.6, then what do we have? 201.8, then what do we have? 179.3, 184.9, and this is 189.1. Okay, so mean is 185.34. So this we can write as 185.34 minus 185 divided by S. S is what? If this is my X, let's say, then S is equal to SQRT of variance of X. In R, variance means the denominator is 1 by n minus 1. Okay, so S is how much? 11.29. So this will be 11.29 by square root of n is 5. Okay, so if we calculate this, 185.34 minus 185 divided by S divided by SQRT 5. So this is our T statistic, 0.067. Okay, so this is 0.067. 0.067. Now step 3 is what? T critical. This is actually that point such that area above which should be 1 minus alpha. Okay, and df is n minus 1. So how do I get this value? This would be qt, that value of t, such that 0.05 should be the area above. So lower dot tail equal to false. Oh, sorry. The decision rule is what? If t is less than t critical. So this point should be such that the area below is 0.05. So it should be qt 0.05, same thing. And df should be n minus 1, that is 4. So the critical point is minus 2.13. So my critical point is, where is the pen? So this should be, this is minus 2.13. Now since T observed is greater than T critical, hence we fail to reject H naught. And that is our decision. Alright. So now if the same thing I wanted to do in R, then I would have conducted a T dot test. Okay, so T dot test will perform a student's T test. Okay, so I have to specify my vector x, and then the alternative is less. Okay, and paired we have to give false. Then also you see, this is the T test df4. Okay, and the sample mean of x is 185.34 and the p value is 1, which means that, okay, mu we have to specify, no? So mu was how much? Mu was 185. Okay, so see, it coincides with our test statistics also. We also obtained 0.067. The same thing is obtained over here. P value is greater than 0.05, so we are we are not rejecting, and this is the sample estimate. Alright, so whatever we did here is actually can be done with one command, that is t.test. Is it clear?
Ma'am, I have a question.
Yes.
In questions where H0 is given as at least or at most, where will the significance level lie?
At least or
At most.
can you give me an example?
Like ma'am, H0 is at least let's say 10. So where will the alpha lie?
Oh, okay. So that again, as I was saying, so you are talking about this situation that H naught mu less than equal to mu naught, something like this.
Yes, ma'am.
Okay, so you would have a rejection rule, right, like specified, right? So and H1 would be mu is greater than some mu naught. Usually what happens, what if the alpha or the rejection rule will be based on whatever is happening over here. So in all the examples that were shown in class, what is usually happening is if there is a greater than sign over here, then usually it is this side, and if it is a less than, then usually this side is happening. Okay, so in whatever example that you are going to do, this rule will only follow, but it is important to remember this is not always the case. Okay, because if let's say your likelihood here, this is less than equal to k, something you are devising, if here there is a, if this has some sort of ratio such that this sign is reversed, okay, so the space where this should happen, this probability of C should be alpha. Okay, so if this is not reversing the, what do I say, the sign over here, then it is it will not change, like in examples. So what I mean to say is that for all the examples that you are going to do, irrespective of whether you have less than equal to or greater than equal to over here, whatever is here, that bound will only follow. But that is not always the case given the Neymer-Pearson lemma. Alright?
Can you please explain with the help of an example? If you can.
Yeah, I can.
Can you check your practice questions? Maybe there is some similar question.
Alright, okay, fine. We'll do that. So let's say this one. So what is this saying? That mean water usage in homes 350 liters in a day. To verify this claim, a study of 200 randomly selected flats was instigated, with the result that average daily water uses of these 200 flats were these. So what is the value of t statistics and decision about the null hypothesis at 5% level of significance? So what do you think this should be? Should it be a z test or a t test?
T test, ma'am.
Yeah, because sample variance is not given. Okay, so here again the t would be x bar minus mu naught by s by root n. Okay, and here let's say
if the sample size is greater than 30, then we need to use t test or z test.
You can use t-test, you can use z-test also. More accurate would be to use a t-test. But if you do not have the matrix provided and if it is greater than 30, then you can go ahead and use the z-test.
Okay, ma'am.
Okay. Alright. So n is 20 and TDF will be 19. Alright. So you find out x bar, what it is. What is the value of x bar? What will be x bar? Okay, so this is y, then mean of y is this thing, 353.8. okay, so again we'll have, let's say 353.8 and minus mu naught would be minus 350. So this would be 353.8 minus 350 by s by root n. S will be how much? Square root of variance of y, or you could rather write it as SD of y, same thing, 21.8478. so it will be 21.8478 by root over 20. So we'll just find it out. Mean y minus 350 divided by SD of y by square root of 20. So this is our test statistic, 0.777. Alright, so this would be 0.777. And what is our alternate hypothesis? We don't know, because a housing society claims that mean water usage is this. A study was instigated. Oh, alright. So mean water usage is this thing. We are not given, we are just told that the null hypothesis is this is the mean usage is close to 350 liters. Now it could be greater than 350 liters, it could be less than 350 liters also. So this is an example of a two-sided test. Alright. So then what will be our decision region? The rejection region will be, so this is the distribution of test statistic. Alright. So if it is falling to on this side or if it is falling on this side, either way we are going to reject. So what we usually do, this area we will take as alpha by 2, this also we take as alpha by 2, and since this is a symmetric distribution, it's a t distribution symmetric about 0, we'll just consider, we'll write it like this, we'll reject H naught if and only if probability if and only if mod t observed is greater than this thing, that is t alpha by 2 n minus 1. Anything then associated with alpha like this, it means that the area above that point is whatever is mentioned over here. So this point is actually T 1 minus alpha by 2, and this is the degrees of freedom. Is it okay? So now we are going to find out what this value is. So this would be, this we'll find out as QT 0. Area above is alpha by 2, that is 0.025. Lower dot tail is false, and we are going to specify the DF. DF is how many flats were listed? 20. So DF would be 19 over here. Alright, this is actually my T critical. So T critical will be how much? I just mentioned QT. Here we have to be careful, in case of a two-sided test, alpha by 2 we have to provide. So this is 0.025. DF is 19, and lower dot tail equal to false. So this is 2.093. T critical is 2.093. What is our T? This is 0.77. So here we have T observed equal to 0.777. Mod T observed is 0.777, which is less than 2.093. Therefore, we do not reject H naught. Is it okay?
Yes, ma'am.
Okay. Alright, let us move on to the next one.
Ma'am, this question is similar to what I was asking.
Okay. So a housing society claims that its average electricity usage in a flat is at least 40 units. To verify this claim, a sample of 12 flats were selected, and their electricity usage per week is observed as follows. Okay, so here H naught is at least 40 units. That is mu equal to 40. It should be greater than or equal to 40, and H1 is mu less than 40. Okay, so all of these one-sided T tests, they are they hold true for these composite hypothesis as well. So here the value of the test statistic is same. So here also T is x bar minus mu naught by S by root n. Okay, so the rejection rule here also, it is if T observed is less than T critical, because this is mu is less than 40. Alright. Just I'll show the intuition behind this. Let's say this is your distribution of x bar. X is following normal mu sigma square. So x bar will also follow normal mu sigma square by n. Let's say this is your x distribution of x, and this blue one is sort of your distribution on x bar with a reduced variance. Is it okay? Now let's say this is your mu. Now if x bar is close to mu, it means difference is 0. What you are trying to say is that x bar should be greater than or equal to 40. Alright, so let's say this is your mu equal to 40. You are expecting x bar to be greater than or equal to 40, something over here, such that this difference you are trying to quantify. Okay, let's say here you have x bar. Anywhere if it falls over here, then x bar is greater than equal to 40, your claim is sort of satisfied, right? But if it falls here, then x bar will be less than 40, right? Now you would want to reject if x bar is way less than 40, some sort of what do I say, some margin you are able to consider. But if it is way less than 40, then only you are going to reject, right? So if I am transforming, so what we do is, when we do this, let's say we are sort of translating this to an axis, we are transforming it such that the variance becomes 1, the spread becomes 1, and this point becomes 0. It is just a shifting of scale and axis, but the directionality doesn't change in this case. Do you get my point?
I'm trying, ma'am.
So this is the intuition behind doing such sort of a thing. If you have something greater than or equal to 40, you would expect it to lie on this side. So you would expect the difference to be greater than 0. But if the difference is less than 0, that is when you are going to reject, right? Here, if it is mentioning that it is at least 40 units, if it is more than 40, then you are okay with it. This is the distribution of x bar, this is 40. If you have 41, 50, the more the merrier. You are not going to what do I say, like this is acceptable to you because you have said that it is at least 40 units. But if it is way less than 40, let's say if it is 20 or 10, then you would say that no, it is not at least 40. This claim is actually wrong. So this rejection region still remains the same. One example that I can give you is that, let's say
So, ma'am, basically in question where at least is asked, at least is given, so the significance level is going to lie on the left side.
Usually, yes.
And if the value comes less than that alpha, basically, so we are going to reject H0 or H1.
See, whatever value you are talking about, that if it is a p value, then we are going to reject H0. So here is your confusion, I think. Let's say here you can, from this thing, you can either calculate the p value or the critical value. So let's say your t observed is how much? You just calculate x bar something. Let's say this is my electricity equal to this thing. let's say this is your this thing, and you are trying to find out the t statistic. So mean of elec minus 40 is the unit that is going to be given by SD of this thing by square root of how many you have, n. So we have 12. Alright, this is my test statistic, minus 3.444. Alright. This is minus 3.444. Now you could have two rules which are essentially the same thing. So rule A is if p value is less than alpha. What will be your p value in this case? In this case it will be probability any distribution t having value lower than your t observed. Okay, so this is probability. So here this you would get by pt. T observed is minus 3.444, lower dot tail equal to true, and df should be 11. Okay, so this is your p value. So if I write this pt minus 3.444 or this thing, let's say, and df is equal to 11, then this is 0.002. This is your p value. Alright, 0.002, which is less than alpha, therefore reject. This is one way. The second way is that reject if t observed is less than t critical. And what is this t critical? T critical is qt 0.05 df equal to 11. So it is qt 0.05 df equal to 11, that is minus 1.79. So reject H naught if t observed is less than minus 1.79. If this absolutely holds true, which it does in this case, here we have minus 3.444, which is less than minus 1.79, and hence we are going to reject the null hypothesis. So what essentially is happening, I'll tell you here. Let's say this is your t distribution. Alright, so this is your minus 1.79. Alright, so area below this is alpha or 0.05. Okay, so if your t statistic or t observed is falling in this region between minus infinity to this thing, then we are going to reject. That was your rule B. Okay, and the probability that, so probability t less than, so what I intend to say is that, let's say your t observed is lying somewhere over here. Okay, in this green point I am showing, let's say t observed is lying something over here. So probability area below this point is this much. So as long as this area remains less than this 0.05, it essentially means that, I mean, can you see the equivalence of these two sentences? P value means that the area below this point is less than 0.005. When I am calculating p value, I am talking in terms of area. And when I'm talking in terms of the critical value, I am looking at these values along the x-axis and taking a decision. So both of these are equivalent things. As long as my t observed is less than the t critical, this p value will also be less than 0.0 alpha, 0.05. If I slide it along this side, then it will increase maybe the p value, but it will remain still below 0.07, 0.05. Okay. So now if I have something greater than 0.05, let's say my p value is greater than 0.05, so then that means that the equivalent t observed is falling beyond minus 1.79. So then we are not able to reject the hypothesis. Is it clear, the equivalence of the two sentences?
I think so, ma'am.
All right.
So basically, if the p-value is going to lie ahead of alpha, then H naught is true.
So p-value corresponds to area. So if that is less than, that is always less than, whichever way it might fall. Okay. So let's say if you have a two-sided test. This is a two-sided test. Okay. This is your alpha by 2 cutoff point, and this is also your alpha by 2 cutoff point, such that this area is alpha by 2 and this area is also alpha by 2. Okay. So now let's say your t observed is something, let's say this point is A, or rather I would give some concrete number to this point, it would be easier. Let's say this is minus 0.57, this is plus 0.57. Okay. Now your t observed, if it is falling here, you are going to reject. Okay. So it is minus 0.47. So probability in case of a both-sided test, p value is actually this area and this area combined. So p value in that case would be probability mod t greater than t observed. That means t greater than this thing or t less than minus this thing. Okay. So if these two, you are adding these two up and it still remains less than alpha, because these two add up to alpha, then you are going to reject. Alright. In case of a right tail test, if you have a right tail test, then this one, let's say this area is alpha, and if your p value is such that your p value will be probability t greater than t observed in case of a right tail test. Okay. So then if t observed is falling over here, your p value would be this right side area, and if this area is less than alpha, then you are good to go. So whenever you are considering p value should always, if it is less than alpha, you are rejecting null hypothesis, regardless of whatever tail test it is. What will depend on the tail of the test is how you are calculating the p value. Is it okay?
Yes, ma'am.
Alright. Fine. So this is done. Let's say this one. So this is also the same thing, but here we have two sample tests. Okay. So how do we do it? There are two manufacturers, A and B. and they are producing 10 LED lights each. So here we have to see that they are independent samples. Okay, and it is known that the lifetimes of LED bulbs tested A are normal with standard deviation 4000, and those tested at B location are normal with 6000. So then what do we have to write? If the manufacturer is interested in testing the hypothesis that there is no appreciable difference in mean life of bulbs produced by either method, then what is the value of the test statistic and conclusion? Alright, so then this one H naught is actually mu1 minus mu2. Okay, so then your test statistic is XA bar minus XB bar minus mu1 minus mu2 by, since sigma A and sigma B are given, then it would be sigma A square by N1 plus sigma B square by N2, and it will follow a normal 0 1 under H naught. Okay, then what is your mu1? No appreciable difference in mean life, and nowhere does it mention that one is better than the other. Is it somewhere better? Okay, to ascertain which is superior, 10 using the first method and sample of 8 using the second. First test is said to be tested at location A and second at B. Lifetime of is normally distributed. It is known that test location, if the in testing, that there is no appreciable mean difference by either method. Okay, so there is no clear-cut instruction that is given by which we can understand whether one is superior or not. Like if the manufacturer is trying to assess superiority, so then our H naught will be mu1 minus mu2 equal to 0 versus mu1 minus mu2 not equal to 0. Alright, so we'll just find out the value of T. So XA bar we'll find out, XB bar we'll find out. NA is given 10, NB is given 8, and sigma A square is given as how much? 4000 square, and sigma B square should be how much? That should be 6000. Alright, then what should be, so we can get the test statistic formula. We'll find out what is the value of T observed, and T critical would be this point. Let's say this is a normal 0 1, so that point in that scale such that area below is alpha by 2 and area above is also alpha by 2, that is 0.025. So for normal 0 1 we know this point is 1.96 and minus 1.96. So the rejection rule is reject H naught if and only if mod of T observed is greater than 1.96. Either this one or probability mod T greater than T observed is less than alpha. This is what? This is nothing but P value. That is probability P greater than T observed plus probability T less than minus T observed. Is it okay? Okay, so we'll just try to figure out what this will be. So this is A and this is B. So we'll find out XA bar and XB bar. Let us find that out. So A is this, okay, and B is this. Okay, so test statistic is mean A minus mean B minus under H0, what is mu1 minus mu2? That is 0. So that will remain as it is, divided by square root of, now sigma A square by N1. So that is 4000 into 4000 divided by 10 plus, how much is this thing? This is 6000. So this would be 6000, what happened? Plus 6000 into 6000 divided by 8. So this is 0.00065. So T observed is actually, so T observed is actually 0.00065, and it is not greater than 1.96. So we are not rejecting H0, but we are accepting H0. Okay, and what is the p value? P value is probability T greater than T observed plus probability T less than minus T observed. So how will we get this p value? P value will get from here. So this would be PT, or this is normal distribution, right? So it will be P norm greater than 0. So let's say if I give this as T observed, okay, so P norm of T observed mean 0 SD1 lower dot tail equal to false. So it will give me probability T greater than T observed, this plus P norm T observed, or rather minus T observed lower dot tail equal to true. So this is the p value is 0.999. So this p value is actually 0.999, which is greater than alpha. Therefore we accept H0, we do not reject H0. Is it clear? Is it okay?
Yes, ma'am.
Okay. Fine. Another way to do this is by directly using R. How can we use this R directly? So we just have to write T dot test. Can you see my R screen? So
Yes.
x equal to A, y equal to B. Okay, here like x equal to A, y equal to B. Alternate will be both sided. Alternative is 2 dot sided. Here you have to write 2 dot sided for both sided. Okay, so once we have that, then mu is what? It should be 0. Alright. And oh, okay, so this is not a t test, I'm sorry. Oh, okay, no, you could do it, but it will not yield the same result, because what we are doing a z test, right? And this is a t test. But even then, I think the values will be the same. Like if let's say this 4000 and 6000 were not given to us, then we could have done a two-sided t-test using this method, and we just had to specify conf.level equal to 0.95. okay, so even though the test is accepting it, this is not equivalent to the z test that I showed, mainly because here we have sigma a and sigma b as known. Alright, but if they were not known, we could have done it with respect to a 2-dot t-test. Okay, so same thing, same question has been given here, but here they have not mentioned the standard deviation. They have mentioned equal standard deviation, which is unknown. Alright, so equal standard deviation which is unknown means that we are doing a sort of pooled variation. Okay, so we are going to use this test. Okay, pooled variance test, df n1 plus n2 minus 2, and this would be the formula that you are going to use. Alright, so let us just try and do it and see if it matches with the 2-dot t-test. So first let us do it here from my R console. So we were doing x equal to a, alternative is two-sided, mu equal to 0, confidence level equal to 0.95, var dot equal to true, or no, equal variance no, was false, and then what we were doing, paired equal to false. So from this test we got this value. If I am running it here, sorry, so this is my t statistic 0.9787867, df is 11.422, okay, p value is 0.348. okay, and this is the sample of estimates. So let us try and see if our estimate is also giving the same result or not. Okay, equal standard deviation, oh okay, equal standard deviation they have said, so variance equal to true. Yes, so df 16, t is 1.08, p value is 0.3192, so we are going to accept it. Alright, but let us find out whether it is matching with what we were thinking. Alright, so the test statistic is how much? Like we mentioned, it should be this one, right? n1 plus x1 bar minus x2 bar. So this is xa bar minus xb bar minus mu1 minus mu2 under h0 is 0, so we are not writing it. Mu1 minus mu2 equal to 0 versus h1 will be mu1 minus mu2 not equal to 0. Okay, so then this is minus 0 by square root of n1 minus 1 into, what was the formula? This thing, s1 square into s1 square plus n2 minus 1 s2 square by n1 plus n2 minus 2. And T critical is also the same thing. That point T alpha by 2 such that area above is 0.025 and the degree of freedom is n1 plus n2 minus 2. So now you see n1 plus n2 is how much? That is 18 minus 2 is 16. So it is matching. Alright. Now this one we'll try and calculate. So XA bar was how much? XA bar was, here we can write 61.65 and XB bar was 60.025 by root over n1 minus 1 is 9 into S1 square, that is variance of A. So if I write variance of A, this is 6.849444 plus this one will be n2 minus 1, that is 7 into variance of B, and that is how much? That is 16.57. So this is 16.57 643 by 16. Okay, so if we just calculate this, let us see what is the value of the test statistic that we get. So here we are doing 61.65 minus 60.025 XA minus XB bar, okay, divided by square root of 9 into variance of A, let's say, plus 7 into variance of B divided by 16, and entire thing within square root. Okay, so this is 0.487. Okay, so this is 0.487, and yeah, and then T critical is how much? T critical would be QT 0.025 lower dot tail equal to false. QT 0.025 lower dot tail equal to false, and DF is how much? DF is 16. This is 2.11. This is 2.11. So since T observed, mod T observed is less than T critical, hence we do not reject H naught. Is it okay? All right. Is there anyone? Okay. So this is also similar. Okay, this is actually an example of a paired t-test. So in order to do it in R, what you have to do, this is your before treatment, this is your after treatment. So if you just do a T dot test and paired equal to true, then you are going to get your test statistic and the p-value, and whether you should accept or reject the null hypothesis. So without seeing anything over here, all the p-values I see are greater than 0.05. So we are going to accept the null hypothesis. Okay, whatever be it, we are going to accept the null hypothesis. Now you have to find out t, and how will you calculate t? That will be with respect to your paired t-test. And how do you calculate that? You get the difference, that is after minus before. Okay, and given sigma square is not given, then what is the test that you are going to use? So then the test statistic would be d bar, mean of before minus after minus before, by SD by root n. Okay, and then the distribution will also be a t, and with df should be n minus 1. Okay, and what is the, is it a right tailed or left tailed test? How will you understand? Who did not know was receiving, decided would know the length of time that the disease lasted was then recorded. If it is effective, so d after minus before, this length of time should be reduced, right? If your medicine has to be effective, then your h naught should be d equal to 0. Before medicine, the length of time the disease prevailed, and after medicine, the length of time that disease prevailed is actually, it is same. And h1 means that after time disease, length of disease prevalence is less than before. So your h1 will be d less than 0. Alright, so you should reject your h naught if and only if t observed is less than t critical. And how will you find t critical? That is that point in t distribution below which the area is 0.05, and the df should be how much? It should be n minus 1. Okay, so just find out t, you get di's before minus after, then get mean di, mean of t, then d bar by s by root n. Okay, and s will be how much? 1 by n minus 1 summation di minus d bar square. Is it okay? Is it clear? Okay, so here also the same thing, time taken before and after, you get the before minus after or after minus before, then you formulate what should be your alternate hypothesis if the safety program is effective. If the safety program is effective, then this time accordingly should reduce or be more, that you have to judge, and then follow the same thing. Is it clear? Is it okay?
Ma'am, actually, I have not yet attempted the assignment. That's why I can't tell right now.
Okay.
I will first attempt and then ask if there is any question on the discussion forum.
Okay, fine. All right. So this is I showed you how the R console looks like, right, in case of a t-test. So here you would have the value of the test statistic, the df, whatever it is, p-value, confidence intervals also they give, and the sample estimates, okay, for a 2 sample t-test and for a 1 sample t-test. So let's say here this is your output, Then related level of significance and the decision about the null hypothesis are as follows. So true difference in mean greater than 0.99% confidence. So here your level of significance is how much? It should be 1%. Okay. However much confidence, 1 minus that will be your level of significance. Okay. And p-value, if it is less than this level of significance, then your decision is rejected. If not, it is accepted. So here it is 1% level of significance, which means 0.01 is your cutoff value with which you should consider. So p-value, is it less than 0.05? No, it is not. Hence, it is accept the null hypothesis. Okay. Similar questions over here in case of a paired t-test. So outcome is given here, which is the following is 2. It's a single sample test about mean from a normal with unknown variance. 2 independent samples about equality of means. 2 independent samples about equality of means from normal but equal and unknown. Or 2 independent sample test about equality of means from a normal with unknown variances. So what should your answer be? So here they are trying to find out mean of differences. So since it is the same thing, so even though you have XA and XB, finally you are basing your assumption analysis on D. Okay, so then D becomes a single sample because these are paired on the same individual. This becomes a single sample test with unknown from normal population with unknown variance, just as I showed over here. So if this is your test statistic, this is the same test as test of a normal mu from a population with unknown variance. So your answer will be this thing. Is it all right?
Yes, ma'am.
Okay. So all right, I think even though this is holding true, to be very accurate, it is a test, it is a 2 sample dependent test. Okay, because you are considering before and after on the same, and what you are testing, you are testing mu1 equal to mu2, that is equality of tests. Alright, so if you have anything like this, 2 sample dependent test testing equality of means with unknown variance, that would be a more exact form. Okay, because it is given it as a paired t-test. Here this D could have been the correct answer, but since it is given to independent sample, it is not a correct answer. Is it okay? Alright. Then here what do we have? Okay. So here we have a machine that...
Can you please show the last slide? How were we able to comment on the variance?
So here what we are doing, since we are testing the difference and no information about variance is actually given here, these are all sample estimates. Pair t-test, if you look at the R console, okay, here you don't have any what do I say, first thing is it is a t-test. So t-test you do when you have unknown variances, it's not a z test, right? Is it okay?
Okay, ma'am.
Alright. So then next we move on to a test for variance. Okay. So here the question is, the machine that automatically fills the juice machine is judged to be effective if standard deviation of the amount of juice in a 200 is less than 0.15. Okay. So effective if it is sigma is less than 0.15. If a sample of, so this is my alternate which I want to believe, and H naught I can specify as sigma equal to 0.15 for my own peace of mind. Alright. Okay. If it is less than 0.15, then it is effective. Now n is 20. Sample variance of this much. So S square is actually 0.025. Alright. Value of the chi-square statistics and its p-value and decision. So statistic is actually n minus 1 S square by sigma square. Alright. So here sigma is less than 0.15. So we'll reject if t is less than chi-square 1 minus alpha by 2. So for chi-square, the thing is, it is a positively skewed distribution. Okay. So this point is chi-square alpha by 2 such that area above this is alpha by 2. And this point, let's say, is chi-square 1 minus alpha by 2. So it means area below it is 0. Or rather alpha by 2. If I just write it as alpha, then this means area below this point is alpha and area above this point is also alpha, but they are not symmetric. This is, since this is a positively skewed distribution. Alright. So the rejection rule will be, since sigma is less than 0.15, this will be reject if t observed is less than chi-square 1 minus alpha and the df is n minus 1. Alright. So we'll just find out here. N minus 1 is how much? 19 into S square is given, sample variance 0.025. So t observed will be 19 into 0.025 by sigma square. Under H naught, what is sigma square? 0.15. So this would be 0.15 whole square, standard deviation, because they are here, they are mentioning standard deviation. Okay. What will be this value? Let us just find out. 19 into 0.025, that divided by 0.15 square. Okay, so this is my test statistics, 21.1111. Okay, and critical value is which one? Chi square 1 minus alpha n minus 1. So it will be chi square 0.95 n minus 1. So how will I find that? It will be q chi square 0.05, area below which is 0.05, and n minus 1 should be 19. So this is 10.11. So this is 10.11. So what do we do? Here we see T observed is not less than or equal to T critical, hence we do not reject H naught. Is it okay? Is it clear?
Yes, ma'am.
Okay. So this one we did. Similarly here also, two different choices of vending machines to test whether variance filled by the two machines are the same. 10 bottles is filled up using first machine and 12 is filled up using the second machine. So then we have to find out the F statistic. Okay, so here we are testing for difference of, here we are testing for difference of variances. Okay, so then F would be how much? F would be 1 by m minus 1 summation xi minus x bar whole square by 1 by n minus 1 summation yi minus y bar whole square. Okay, so sample variances as 0.14 and 0.28. So this would be 0.14 by 0.28. So F value is actually 0.5 and the critical value is F m minus 1 n minus 1. Okay, and here also the same thing, equal variance, whether variance are same. So H naught is actually sigma A equal to sigma B and H1 is sigma A not equal to sigma B. So our rejection region will be reject H naught if and only if F is greater than F m minus 1 n minus 1 alpha by 2, or if F less than F m minus 1 n minus 1 1 minus alpha by 2. So F distribution is also like this way. Okay, so we'll reject if F is falling in this region, such we have to find out this point such that area above is 0.025 and this point such that area below is 0.025. Okay, and if F is falling in this area or in this area, then only we are going to reject H naught. Is it true or is it okay? Okay, so F we found out is 0.5. Now we'll have to find out this area. So M was how much? 10 bottles and 12 bottles. So M and N minus 1 we have to find out. So let us find out QF. M minus 1 is how much? 10. So 9 and 12. 11. DF1, DF2 we found out. F distribution, small f. So DF1, DF2 we found out. And then area below should be 0.025. 0.025. So that is 0.2555. So this one, if M minus 1, N minus 1, 1 minus alpha by 2 is actually 0.255. And if we just put this thing and put a lower dot tail equal to false, then we are going to get the upper critical point. So this should be 3.58. So here we are seeing ours is 0.5. It is not below 0.255. It is lying somewhere here. This is 0.255 and this is this is 3.58. This point is 3.58 and ours is lying in between. Thus we are going to accept H naught. And this is our answer. Null hypothesis of equal variance cannot be rejected. Is it okay? Okay. Here also same sort of thing is given. Random selection of 12 patients were given a medicine. Another group of 10 were given placebo. Length of time treated with medicine, treated with placebo. Test if the variance of the medicine is more than the variance of placebo. So we have to, the H naught is sigma A medicine is equal to sigma placebo and H1 is sigma A or medicine is greater than sigma placebo. So we can just directly go ahead with the F test, okay, just like this, and we have to, since this is a one-sided test, if we are taking medicine, like medicine by treatment, like if we are considering F medicine by F placebo, then sigma M greater than sigma P means that we are going to do a right sided test. Alright, so we will reject if this T is greater than F critical, that M minus 1, N minus 1 and alpha by 2 we are going to define. And if we want to do it straightforward with respect to in R, then we just have to do a var dot test. Var dot test, just input, okay, to compare two variances. Alternative we have to give whichever is less, or so first we have to specify if X is treatment and Y is placebo, then variances of treatment is greater than placebo, then we have to specify alternative as greater than. Alright, so once we do this, first we'll write treatment, then we'll write placebo, then we'll give greater, and then just the confidence level that we have to do, we have to give, and ratio equal to 1. Okay, and then it will readily give you the sample variances, ratio of the variances, F statistic, and degrees of freedom for numerator, denominator, p value. From that you can take a call. Is it all right? there are no more questions, then I'm going to close today's session. Please let me know
Okay,
if you
ma'am.
have doubts.
Ma'am, I will ask on the discussion forum.
All right, fine. Okay. Thank you so much for joining then. Have a nice day. Bye bye.